Hi, I'm going to give you a brief understanding of pH. That way you can understand readings about acid rain or acid fog. All right, let's get started. So first of all, you should know that water actually auto-dissociates or auto-ionizes on its own, and that happens naturally. So what that means is if you were to look at this example here, two water molecules, one water molecule actually donate a proton to another water molecule, and that would give you a hydronium ion and a hydroxide ion. And this actually happens about 2 in 1 billion water molecules. So it's actually not, in percentage wise, it's not a large percent of the water that actually ionizes, but you can actually measure it. And if you were to say, for example, take 1 liter of water, if you were to take 1 liter of water, you would find 1 times 10 to the negative 7 moles of hydronium and 1 times 10 to the negative 7 moles of hydroxide. That's just the amount you would get for that 2 in 1 billion. And by the way, when I talk about brackets, I'm going to start using brackets. That's just a shortcut way of expressing molarity. So for example, if you see brackets around hydronium, it just would be like a molarity. So for example, 0.15 molarity. So in a neutral solution, and neutral would be like pure water, you would expect that your hydronium ion concentration would equal your hydroxide concentration, which equals, for both of them, 1.0 times 10 to the negative 7 molar. And we have a term for this, it's Kw, which is your water dissociation constant. So if you were to actually multiply the two values together, your hydronium ion concentration to your hydroxide ion concentration, you would get 1.0 times 10 to the negative 14. But the interesting thing is that this is true for all aqueous solutions, every single one of them. So this Kw, or your water dissociation constant, is a very powerful tool in number. So definitely remember this one, definitely know where to pull it out and use it. All right, so I'm going to box it for you here. So when we want to figure out if something's acidic or basic, other than using a litmus paper, we can actually measure or calculate, and we would compare our values to the neutral solution. So if it's an acidic solution, you would expect to have more hydronium ions than in a neutral solution. So that would be the concentration of hydronium should be greater than 1.0 times 10 to the negative 7. And that would mean your hydroxide would have to be less than 1.0 times 10 to the negative 7. Same thing, in a basic solution, you would compare it to your neutral solution, and you would expect that the hydroxide, not the hydronium, but the hydroxide should be larger, 1.0 times 10 to the negative 7, and your hydronium should be less. So you can actually determine concentrations based on your Kw. So the first thing is pull out that magic number, which is just Kw equals 1 times 10 to the negative 14. Okay, which equals your concentration of hydronium times your concentration of your hydroxide. That would be your step number 1. Step number 2 is just rearrange the equation depending on what you're solving for. So if you're solving for hydronium, for example, or hydroxide, this is hydroxide, you would divide everything by the hydronium, right? So that means you would divide the left side of the equation by hydronium. So that's 1 times 10 to the negative 14 over your hydronium. And you can divide the right side by hydronium, and that would just leave you with your hydroxide. And then you could just plug in values at that point. So for example, if you were given a hydronium concentration of times 10 to the negative 3, you want to find the hydroxide concentration, you would just plug in the value. So it would just be times 10 to the negative 14 divided by times 10 to the negative 3 will give you times 10 to the negative 11 molar. Okay, so it's a very simple calculation. Okay, so let's do another example. So for a solution that has a hydronium concentration of 1 times 10 to the negative 5, what would be the hydroxide concentration? So again, you pull out your water dissociation constant. I'm going to rearrange it. So I'm going to put hydronium on the bottom for this example. And then I'm going to plug in the value given to me. And that leaves me with 1 times 10 to the negative 9. And the question for that is, would you expect the solution to be acidic or basic? Should be acidic. Now, why did I say acidic? Again, you compare the value to neutral. In an acidic solution, you would expect the concentration to be greater than 1 times 10 to the negative 7. Notice it's negative 7. Negative 7 is smaller than negative 5. So 1 times 10 to the negative 5 means I have more hydroniums than I do at the neutral. And the same thing is I should have less hydroxide in an acidic solution. Then times 10 to the negative 7 and times 10 to the negative 9 is much smaller than a neutral solution. So a pH scale is a special way to indicate how acidic or basic solution is. So a pH scale is just basically pH equals the negative log of your hydronium ion, right? Notice it's pH, not POH, it's pH. So for example, if I were to stick in 1 times 10 to the negative 3 concentration, I would get pH equal to 3. And this is actually just a simple property of logs, so the log of 10 to x just equals x. And so yes, those negative signs cancel out. I have times 10 to the negative 3 and a negative log, the negatives cancel out, and I'm just left with pH 3. So it's actually a very simple calculation, which is nice, and you can always plug it in your calculator too, but you should just know that the math should be that simple. So keep in mind that this is a logarithmic scale. So what that means is for every decrease of 1 unit on the pH scale, that corresponds to an increase in hydronium concentration by a factor of 10. So a pH of 4 means you should have 10, if you put in the negative log, that means you have a concentration of 1 times 10 to the negative 4. That would be your concentration. And if you were to represent that with balls, it would be 1 dot. So each dot represents 10 to the negative 4 moles of hydronium per liter. Now if I have a pH of 3, that means I have times 10 to the negative 3. And notice the ball representation. I have times 10 more balls. 10 more balls. Total times 10 more balls. Now if I were to do pH of 2, which is, I have a concentration of times 10 to the negative 2, I would actually have 10 times 10. So it's a significant difference between each pH level. It's not a slow incremental change. They're factors of 10. So keep that in mind when we talk about acid rain, right? Acid rain, if you talk about changing the acid rain from a pH of, say for example, 5 or 6, say pH of 6 down to a pH of 3, you're talking about 10 times 10 times 10, 3 tens. So it's a huge difference. Okay. So let's go back to our pH scale. So again, pH equals the negative log of your concentration of hydronium. And again, remember in neutral pure water, your hydronium concentration equals your hydroxide concentration, which is 1 times 10 to the negative 7. And so if we were to take that neutral solution, your pH equals the negative log of 1 times 10 to the negative 7. So that equals 7. So if I were to look at my pH scale, neutral right here in the purple, is 7. Based on what we already know. Now, so that's right in the middle. Now if I go to the left of the pH scale, I'm increasing in acidity. So I'm decreasing in numbers here. I'm increasing in acidity. And that's again, it's just because of the negative log. So I have a higher concentration, you can see on the bottom. So I have a higher concentration of hydroniums or protons. I have a higher concentration of protons. I have a lower acidity, or higher acidity, I'm sorry. Let me repeat that. I have a higher acidity or a lower pH. Okay. Same thing with basicity. As I increase, if I go to the right, I increase basicity. That means I have a lower amount of hydroniums and a higher amount of hydroxides. I can show you how this looks like with just things that you know in your everyday life. So, for example, you might have worked in the lab with sulfuric acid. Sulfuric acid would burn you, it melts metals, it's dangerous. And it has a pH of about 1. And your battery acid, this is car battery acid, by the way, not your batteries, alkaline batteries, those are actually bases, but your car battery is a pH of 0. Lemon juice is a pH of 2, right, which is very similar to hydrochloric acid in your stomach. And then rainwater, which is clean rain right here in the blue, is about 5.6. Is a little bit acidic, and that's just because you have carbon dioxide actually dissolves the water, giving you carbonic acid. And your acid rain lake is actually 4.5 or 4.2, so it's, you know, less, even more acidic. And pure water is neutral. And then seawater is a little basic, it's about pH of 8. And then you have baking soda, which is pH 9. Ammonia you might use for cleaning is pH 11. Soapy water is 12. Bleach is 13. And your liquid drain cleaner is pH of 14. Alright, well that was a brief overview of the pH scale and how to use it. Alright, I will see you guys next time. Bye-bye.